Traditional building demolition is coming to an end. The construction industry is moving away from the linear take, make, dispose economic model. In 2026, the industry utilizes buildings as material banks, or BAM. This system organizes structural assets so that every component is tracked for future recovery. This is the result of reversible architecture. Every beam and panel can be extracted intact and reused in a different configuration. But reaching this stage required solving a paradox. During the 2010s, the original promise of free, downloadable open-source architecture failed to scale in the real world. To see why, we have to look at where modular construction began. The concept traces back to the Industrial Revolution and Joseph Paxton. Paxton's 1851 Crystal Palace was the first structure to fully implement industrialized modular prefabrication. However, it was tied to a high-carbon production cycle, fueled by the coal-burning heavy industries of Britain's Black Country. By the 1960s, architects like N. John Haberkin and Walter Siegel tried to democratize this process. They separated permanent support structures from customizable infill and used modular timber grids to let people build their own homes. These ideas stalled during the lost decade between 2012 and 2022. The attempt to apply the zero marginal cost philosophy of software to physical materials resulted in a decade of industry stagnation. The failure was driven by three specific barriers: physical material tolerance, proprietary software lock-in, and economic vulnerability. Building a fully circular construction system by 2026 required engineering solutions for these three specific open-source failures. The first barrier is physics. Digital code is identical every time it's copied, but physical materials interact with gravity, moisture, and variable loads. Wood is an anisotropic material. It shrinks, expands, and bears weight differently depending on the direction of its grain and the local humidity. Early models like WikiHouse relied on traditional wood-on-wood joints. Under dynamic loads, these suffered ductile shear failure. Engineering shifted to the WikiHouse Skylark cassette paradigm. A hollow 39-kilogram timber block can now support a 13-ton vertical load. However, pure timber systems still face a physical limit. The joints eventually degrade after repeated assembly. The 2026 solution is hybrid architecture. The vulnerable wooden joints are replaced with indestructible T-slot 2020 aluminum extrusions. To make this work at an industrial scale, the industry adopted the OpenStructures standard. This defines a rigid geometric grid. The aluminum extrusions follow this 20mm spatial logic, allowing parts from different manufacturers to lock together perfectly. Combining carbon-negative mass timber with infinite life-cycle aluminum nodes solves the physics problem. It allows structures to be taken apart and rebuilt without damaging the materials. Solving the hardware was only half the battle. How do you manufacture these micro-precise hybrid joints in a local workshop without errors? Manual offsets in CAD files cannot account for real-time local humidity or specific structural loads. If the wood expands by a fraction of a millimeter, the joint simply won't fit. Computational design and advanced Raven AI now automate this entire process. They dynamically adjust the microgeometry of the joint. Through smart material simulation, the AI cross-references weather data and energy models to calculate how the material will behave before it is milled. The AI modifies the CAM files down to 0.1 millimeter precision. The pieces fit together accurately the moment they leave the CNC machine. The second digital barrier was proprietary lock-in. In 2022, a major BIM cloud server crash paralyzed architecture firms worldwide, stopping work on thousands of projects. True open-source production requires software interoperability that is immune to corporate server outages. The industry adopted the Model Context Protocol, or MCP. It functions as a universal connector. MCP allows AI agents to verify joints against local building codes in real time, providing production data without locking users into a single software vendor. AI manages the microphysics of material tolerance, while MCP removes data monopolies. Together, they create a frictionless digital-to-physical pipeline. Digital precision is only useful if there is a scalable economic model to manufacture the components. The traditional industrialized model relies on centralized gigafactories. This PETO system, products in, trash out, requires high upfront capital and generates heavy emissions. The Fab City network shifted this to a DIDO model, data in, data out. Global design data flows to local manufacturers who use regional resources. The 2026 Microfactory provides the exact hardware needed for this shift, packing an entire automated production line into a container. Setting up these automated production containers cost under £100,000. It allows local SMEs to manufacture standard-compliant components close to the building site. But there was one final hurdle: trust. How do governments and banks verify that a building made in a shipping container is safe? The solution to this trust gap is social franchising. The central open-source organization acts as the franchisor. They provide the certified engineering, brand trust, and legal code compliance. Local communities act as microfranchisees. They operate the microfactories, providing local labor and sourcing regional materials, while retaining the capital within their own economy. Microfactories provide the physical tools, and social franchising provides the economic trust. This combination makes open-source architecture commercially viable. When hybrid nodes, AI precision, and local microfactories are combined, they enable 100% reversible architecture. However, once a building is taken apart, the industry must be able to track and value millions of individual components. This is achieved through material passports. These digital records log the ISO compliance, carbon metrics, and U-value ratings for every component. Material passports allow components to retain their financial value. They can be traded in secondary markets with full transparency, ensuring they never become waste. These liquid markets enable a new financial model: component lease layer. Building owners no longer need to purchase mass timber cassettes or aluminum nodes. Instead, they lease them from the local Fab City network. This creates building as a service, or BaaS. Architecture shifts from a static capital expense into a fluid operational expense. In this system, a structural cassette can be extracted from an aging structure and immediately slotted into a new, completely different architectural design. Open-source architecture in 2026 is an integration of material physics, AI computation, and circular economics. It provides a technical and financial framework for building without net resource depletion.